Image information signals on the screen and voltage signals on the oscilloscope. Figure 7.8. Composite video signal and its image information. A. Image with vertical track bars on a white base. B. Reverse information with white bars on black ground. The two examples considered in Figure 7.8 illustrate how composite video signals correspond to visual information. In Figure 7.8a, the video signal corresponds to a line of sight for an image with a black vertical bar below the center of a white frame. In Figure 7.8b, the black and white values in the image are reversed from those in Figure 7.8a. These signals are shown with their positive alignment polarity. But the same idea applies with negative alignment polarity. On the left in Figure 7.8a, the camera signal obtained through active viewing of the image is initially at white level, corresponding to a white background. The scanning beam continues its advance across the white background of the frame, and the signal continues at the same white level until it reaches the center of the image. When a black bar is displayed, the video signal changes to black level and remains there while the entire width of the black bar is displayed. Then the amplitude of the signal changes to the white level, corresponding to the white background, and remains at that level while the forward motion of the image towards the right side of the image is completed. At the end of the visible trace, a horizontal blanking pulse brings the video signal amplitude to black level to initiate trace repetition. After repetition of the trace, the forward viewing motion begins again on the next horizontal line. Each successive horizontal line in the even and odd fields is paid in this way. As a result, the composite video signal corresponding to the entire image contains a sequence of signals with a waveform identical to that shown in Figure 7.8a for each active horizontal viewing line. For the image in Figure 7 to 8b, the idea is the same. Still, the camera signal corresponds to a white vertical bar below the center of a black frame. This signal starts and ends at the black level and is at the white level in the middle. These are all simple image types, but their correlation can be extended to images that have any distribution of light and shade. If the pattern contains 5 vertical black bars against a white background, the composite video signal on each horizontal line will include 5 rapid variations in amplitude from white to black. As another example, for example, the pattern consists of a horizontal black bar across the middle of a white frame. Thus, most of the horizontal lines will contain white image information during the entire trace repetition period. The camera signal amplitude will remain at white level except during the blanking interval. However, for horizontal lines that span the black bar, the camera signal is generated at black level. Typical voltage of video signals. An actual image consisting of elements that have different amounts of light and shade with non-uniform distribution in horizontal lines and through vertical fields. If there is movement in the scene, the video signal contains a sequence of voltages that change continuously. Within each line, the camera signal amplitude varies for different image elements. In addition, the waveforms of the camera signal for the lines will change in the field. The resulting waveforms are shown by oscilloscope images of a typical video signal in Figure 7.9. This signal is for the control grid of the picture tube. It has an amplitude of 100 volts peak to peak and negative alignment polarity. Figure 7.9. Oscilloscope images of composite video signals. Shown with downward alignment at negative polarity. A. 2 horizontal lines with image information between the discharge pulses H sweep of the inside of the oscilloscope at 15,750 divided by 2 equals 7.875 Hz. B. 2 vertical image information fields between discharge pulses V inner sweep of the oscilloscope at 60 divided by 2 equals 30 Hz. Waveforms in an oscilloscope. When you look at oscilloscope patterns, usually the signal variations are not clear because they vary with movement in the scene. However, the oscilloscope trace will lock for H discharge and alignment pulses at a steady rate of 15,750 Hz or for V pulses at 60 Hz. It is preferable to set the inner horizontal sweep frequency of the oscilloscope at half this frequency, to display a video signal for 2 lines, as in Figure 7.9a, or for 2 fields as in Figure 7.9b, so each cycle is shown as large as possible and with balance during the emptying time. Line rate. If the oscilloscope sweep is set to 15,750 divided by 2 equals 7,872 Hz, you will see 2 H lines of the video signal, Figure 7.9a. If the scene shows people walking across a room, as an example of horizontal motion, variations in the camera signal move horizontally. Variations in the camera signal move across the oscilloscope screen between H pulses. Field rate. If the oscilloscope sweep is 60/2 equal to 30 Hz, you see 2 video signal fields, Figure 7.9b. Any vertical motion in the scene is seen as movement in the variation of the camera signal across the trace between the alignment pulses. The longer lines across the top and bottom of the vertical alignment in the oscilloscope pattern are caused by horizontal alignment. You do not see equalization pulses in this pattern because the oscilloscope is locked to the vertical viewing frequency. To see the scanning pulses and the teeth in the vertical pulse, you must set the inner sweep frequency of the oscilloscope to 31,500 Hz or to an additional multiple. Typically, the horizontal sweep of the oscilloscope must also be extended. Oscilloscope waveforms and image information. See Figure 7.10. The image in Figure 7.10 with horizontal and vertical bars is called a crosshatch pattern. This type of image produces similar camera signal variations for horizontal and vertical viewing. However, the main application of the crosshatch pattern is to check the linearity of horizontal and vertical alignment for equal spacing of the rods. The crosshatch pattern is also used when convergence adjustments are made to color image tubes. In Figure 7.10b, the oscilloscope waveform shows 2 H lines from the camera signal because the inner sweep frequency is 8,775 Hz. These variations correspond to the vertical bars in the figure. In Figure 7.10c, the oscilloscope waveform shows 2 vertical fields. Figure 7.10. How the waveforms of video signals relate to image information. A. Crosshatch pattern on the picture tube screen. B. Horizontal image information with V alignment pulses. The inner sweeping frequency is 30 Hz. These camera signal variations correspond to the horizontal bars in the image. On most oscilloscopes, the 30 and 7,875 Hz positions are marked inner sweep frequency switches as V and H for televisions. This makes it easy to switch between video signals for 2H viewing lines and for 2V viewing lines. Image information and video signal frequency. Camera signal frequencies vary from around 30 Hz to 4 MHz. Note that 30 Hz is on the low end. This is an audio frequency, and 4 MHz on the high end is actually a radio frequency. This wide frequency range makes the video signal a wide field signal. It spans a range of approximately 17 octaves. The camera signal has very fast changes in a line because horizontal viewing is fast. Specifically, a 4 MHz signal represents a change in amplitude between 2 consecutive image elements that takes 0.25 microseconds in horizontal viewing. Note that the 4 MHz limit is simply a legal limitation imposed by the 6 MHz channel of the television transmitting station. In vertical viewing, Camera signal variations have much lower frequencies because the viewing speed is slower. A 30 Hz signal represents a change in amplitude between two consecutive fields that repeat at a rate of 60 Hz. Frequencies lower than 30 Hz can be viewed as a change in direct current, DC, level. Video frequencies included in horizontal scanning. In the display board pattern in Figure 7.11, the square wave signal at the peak represents variations. The camera signal is a composite video signal obtained in a single horizontal line view. It is desirable to obtain the frequency of this square wave. The frequency of camera signal variations is very important in determining whether a television system can transmit and reproduce appropriate image information. To determine the frequency of any signal variation, the time for one complete cycle must be known. A cycle includes the time from one point on the signal waveform to the next consecutive point that has the same magnitude and direction. So frequency is the inverse of period. For example, the viewing period for one horizontal line is 1/15,750th of a second, and this means the line's viewing frequency is 15,750 Hz. However, the variation of the camera signal in a horizontal line needs to have a shorter period and a higher frequency. Note that one complete cycle of the camera signal in Figure 7.11 includes information in two adjacent image elements, one white the other black. Only after viewing the second rectangle does the camera signal actually have the same magnitude and direction as at the start of the first rectangle. So, to get the frequency variation of the camera signal, we have to find how long it takes to scan two consecutive squares. Time is the period for one cycle of the camera signal. We can now calculate the period of one complete cycle of the variation of the square wave camera signal in Figure 7.11. The period for horizontal line display is 1/15,750th or 63.5 microseconds, including tracking and retrace. By knowing the horizontal emptying time is 10.2 microseconds. The remaining time for visible tracking is 53.3 microseconds. This is the time it takes to line up all the image elements in a line. All 12 rectangles in one line are paid in 53.3 microseconds. The smaller t time required to rotate two squares, namely 2/12ths or 1/6, is 53.3 microseconds. So, t equals 1/6 times 53.3 microseconds equals 8.8 microseconds. The period for one complete cycle of a wave signal is t. And the frequency f is equal to 1/tf equals 1/t equals 1/8.8 microseconds equals 0.11 MHz in Figure 7.11. The frequency of variation of the square wave camera signal shown at the top of the checkerboard pillar is 0.11 MHz. Typical image information. When a typical image is displayed, the scattered areas of light and shade do not produce a symmetrical square wave signal. However, differences in light and shade correspond to changes in the amplitude of the camera signal. The frequency of variations in the resultant camera signal always depends on the time required to view adjacent areas with different light values. When large targets with a constant white, gray and black level are viewed, the corresponding camera signal variations have low frequencies. The reason is the long time between changes in amplitude. Smaller areas of light and shade in the shadow are displayed at higher video frequencies. The highest signal frequencies correspond to variations between very small image elements within a horizontal line, especially the vertical edges between a white area and a black area. Frequency of videos joining vertical marketing. At the opposite extreme, Signal variations corresponding to adjacent image elements in the vertical direction have low frequencies because the vertical viewing rate is relatively slow. The variations between one line and the next correspond to a frequency of approximately 110 kHz. Slower changes over greater distances in vertical viewing occur at lower frequencies corresponding to variations in light levels between two successive fields. Frequency of video and image information. See Figure 7.12, which shows the amount of image information related to the video frequencies. The main body of the image in Figure 7.12a, shown in Figure 7.12b, with only large areas of white and black. These video frequencies extend to 100 kHz. However, details with sharp edges and outlines are filled by high video frequencies from 0.1 to 4 MHz as shown in Figure 7.12c. Note that the building curtain is reproduced in Figure 7.12b, but the stripes and small letters require high-frequency reproduction in Figure 7.12c. A practical and interesting application is that it is much easier to obtain a sharp image and a very close view of the image than with a long view. An example is a close-up that only shows a human face. However, the individual hairs in the eyebrows are not very small, relative to the width of the image. So this image information does not require a frequency that is too high and means reproduction can be sharp and clear. In a long shot, minute details of the scene are too small to reproduce. Also in color television, close-up scenes and backgrounds look good because the video frequencies of image information are relatively low, compared with those in long-shot views. Typically in most receivers, the image information included in the television picture is only for video frequencies up to close to 0.5 MHz. Maximum number of image elements. If we consider a checkerboard pattern as in Figure 7.11, with more rectangles, the maximum number of image elements can be calculated by dividing each rectangle into one element. Then the total number of elements in the area is equal to the maximum details in a horizontal line multiplied by the details in a vertical row. However, horizontal and vertical details must be considered separately in a television image due to the viewing process. For the horizontal breakdown, the problem lies in how many elements fit into the high frequency limit of the 4 MHz video signal. Vertical details include the question of how many elements can be separated by display lines. Maximum horizontal breakdown. Working in the same way as in the previous section, we can obtain the number of elements corresponding to 4 MHz, in order to show the maximum number of image elements in a horizontal line and the smallest possible horizontal detail size. The period of one complete cycle for one variation of a 4 MHz signal is 1 in brackets 4 times 10 to the 6th power. Seconds equals 0.25 microseconds. This is the time required to zoom in on two adjacent image elements. Since two elements can be paid in 0.25 microseconds, 8 elements can be paid in 1 microsecond. Finally, 8 times 53.3 equals 426 image elements can be displayed over the entire active line period of 53.3 microseconds. If there were 426 squares in the horizontal direction in the checkerboard pattern in Figure 7.11, then the resultant camera signal variation would produce a 4 MHz signal. Figure 7.12. Effect of video frequency on image reproduction. A. Normal image. B. Only large areas in the image are reproduced at low video frequencies up to 0.1 MHz. C. Only important parts are reproduced with high video frequencies between 0.1 and 4 MHz. utilization ratio and vertical detail. Each viewing line can represent at most only one detail in the vertical deflection. However, a display line can indicate no vertical detail at all by completely omitting a vertical detail. Also, two lines can straddle one image element. Thus, the problem in establishing useful vertical detail is in determining how many image elements can be reproduced, given a known number of viewing lines. The number of payment lines that are useful in expressing vertical details divided by the total number of visible payment lines is the utilization ratio. Theoretical calculations and experimental tests show that the summary utilization ratio is from 0.6 to 0.8 for different images with typical image content. As an average, we can use 0.7. Now the maximum number of possible vertical image elements can be determined. The number of visible lines is 525 minus those paid during vertical emptying. With a vertical blanking time of 8%, the number of lines blanked in the entire frame is 0.06 x 525, or approximately 42 lines. Some of these lines occur during repetition of the vertical trace, and others are drawn at the top or bottom of the frame, but all are blank. So what remains is 525 minus 42 equals 483 visible lines. With a utilization ratio of 0.7, the number of lines that are useful in showing vertical details is 483 times 0.7 equals 338 lines. This price represents the number of effective payout lines. Therefore, the maximum number of vertical details that can be reproduced with 483 visible viewing lines is about 338, the exact value of which depends on the utilization ratio. Total number of image elements. On the basis of previous calculations, the maximum number of image elements possible for the entire image is 426 x 338, or about 144,000. This number does not depend on the size of the image. A single frame of 35 mm motion picture film has approximately 500,000 image elements. The smaller 16 mm frame contains as many as a quarter, or about 125,000. So televised reproductions can have nearly the same amount of detail as seen on 16 mm moving pictures. Direct current components of video signals. Besides continuous amplitude variations for each image element, the average value of the video signal must correspond to the average lightness in the scene. Otherwise, the receiver cannot follow changes in light. As an example of the importance of light level, the alternating camera signal for a gray image element on a black background is the same as the signal for white on a gray background. Assuming that there is no average brightness information to indicate changes in the background, the average level of a signal is the arithmetic average of all instantaneous values measured from the zero axis. In Figure 7.13a, the average level is higher than in Figure 7.13b, because variations in the camera signal have higher amplitudes. Now it is important to remember that the average value of any signal variation for a complete cycle is its direct current component. Thus, the current component is direct current in Figure 7.13a, closer to black level than in Figure 7.13b. Although it is depicted here for a single line of sight, the required unidirectional component of the video signal is its average value for the complete frames. Because the background information of the frames represents the brightness of the scene. If the average value or direct current component of the video signal is close to the black level as in Figure 7.13a, the average light is dark. Variations of the same alternating current signal in Figure 7.13b has a brighter background because the direct current, DC, axis is farther from the black level. The distance between the mean axis and the blanking level is called the pedestal height of the video signal, as shown in figure 7.13b. The signal for a light scene has a greater peak height than that for a dark scene. Figure 7.13. Video signals with the same alternating current variation but differing in level about the mean. What is depicted is only one line of a complete skeleton. A dark scene with an average value that is twice the black level. B. Bright scene with average values far from black level. Note that an incorrect direct current level produces false light. This effect is depicted in figure 7.14. Without a direct current component, the image information here is too dark. This image requires a higher focus due to the white background. The transmitted signal has the correct direct current level, but it can be lost through capacitive coupling in the video amplifier. Figure 7.14. Inappropriate bright effect without the required unidirectional component. The image information is too dark because the background is white. In a monochrome television, a faulty direct current component simply causes inappropriate brightness. However, in color television, a direct current component is needed to reproduce the correct colors. Gamma and contrast in images. Gamma is a numerical factor used in television and film reproduction to indicate how light values are expanded or suppressed. Connect to figure 7.15. The exponent of the equations for the curves shown is called gamma. The numerical value of gamma is equal to the slope of the straight line part of the curve where d it rose sharply. A curve with a gamma of less than 1 bends downward as in figure 7.15a, with the greatest slope occurring at the start, and a relatively flat section occurs at the tip. If gamma is greater than 1, the curve bends upward as in figure 7.15b, and the slope at the beginning is flat while at the end it is sharp. With a gamma of 1, the result is a straight line as in figure 7.15c, and the slope is constant. A gamma of 1 implies a linear characteristic, i.e. no excess light value. When gamma is greater than 1 for the white part of the image, the resulting image appears contrasty because the increase in white level is magnified by the sharp slope, emphasizing the white parts of the image. Commercial live images shown in darkened theaters have this high contrast appearance. Gamma values smaller than 1 for the white parts of the shadow suppress changes in white levels to make the image appear smoother, with gradients in gray levels more pronounced. For each component in a television system, a gamma signal can be assigned to describe the shape of its response curve and contrast characteristics. As a typical example, picture tubes have the control characteristic curve depicted in figure 7.15b. The video signal voltage is always on the control grid of the picture tube with the polarity required to make the signal variations in the white part of the picture fall on the part of the response curve with a steep slope. As a result, a variation in the amplitude of the video signal at the white level results in a larger change in the beam current and a darker screen brightness. The image tubes emphasize the white parts of the image, means with a typical gamma value of 2.2 to 3.5. Commercial films also have a gamma greater than 1, with the average value being 1.5. Amplifiers that use linear operation have a gamma that is very close to unit. The straight line response shows that the output signal voltage is proportional to the input signal voltage, i.e., no signal level is suppressed. However, if desired, an amplifier can be made to operate above the curved portion of its switching characteristic curve by shifting the working bias. A nonlinear amplifier can be used as a gamma control stage. A gamma value of 0.4545 offsets 2.22 to give an overall gamma of 1. Figure 7.15. Gamma characteristics. A. Visible eye response. Gamma is less than 1. B. The control lattice characteristic of the gamma tube is equal to 2.2. C. Linear characteristics of an amplifier. Gamma is equal to 1.